Okay, so this class, we have our final on Wednesday. Anybody know the time? Okay. Okay, that's good to know. Exam 5 is Wednesday. 2 to 4. I mean, it's on everything, but the recent stuff that we've done, what do we do before column buckling? I guess stresses and beams. Yeah, so yeah, column buckling is the only new thing. What? It could be. You never know. I would say it's very likely that there's going to be a statically indeterminate system problem of some kind on this. So listen up. So exam 4, number 1. Oh, it only had one number, I think. Okay, so we have a column. And there are 2 external loads, a quarter of the way from the top down to the bottom. Yep. So, yeah, let's do it. So if I do a free body diagram, I'll call this A and this B. So we know that we have 2 horizontal point forces at the ends. I'll call that RA and RB. And we have the torque going this way of 1500. And the horizontal force of 10,000 going this way. And then we have the 2 point torques at the end. So I'll call this one torque A and torque B. And the distances are 1.5 meters there. And 0.5 meters there. Okay, so first we do the statics. So from the free body diagram, Newton's second law says RA0 plus negative 10,000 0 plus RB0 is equal to zeros. So that gives one useful equation, RA plus RB is equal to 10,000. And then the moment equation about the x-axis, so we have TA plus 1500 plus TB is equal to 0. And so torque A plus torque B is equal to negative 1500. Now we're done with the statics, and we can't solve for anything, so we know it's a statically indeterminate system. So now we have to figure out what the internal loads are. We know that we're dealing with tension, compression, and internal torque. So those are the only internal loads we have to calculate. So how many cuts do we have to make? So, yep. So we're doing now the internal loads. Because this is statically indeterminate. Okay, so there's 2 cuts. Cut 1 is for x values between 0 and 1.5. And on this cut, we have RA and torque A. And then we haven't gotten to the 2 external loads yet, so now we just have the internal tension T and the internal torque, fancy T. So Newton's second law says RA 0. You don't have to do this stuff as vectors. You can just do it as scalar equations, but RA 0 plus T 0 is equal to zeros. And so for all of the x's that this cut represents, T is equal to negative RA. And then the moment equation about the x-axis, we have torque A plus internal torque is equal to 0. So the internal torque is equal to negative torque A. So we have this and this. Those are not equations yet to help us solve the system. This is just telling us what those internal loads are, so then we can use those in the macroscopic deformation equations. Because we know that the total length can't change, and we know that over the whole length, the angle of twist has to be 0. Okay, so these are valid for x between 0 and 1.5. And now cut 2 for x between 1.5 and 2. So we still have these forces, these loads at the end. We have RA and torque A. But now we've gotten to the, we're past those 2 external loads. So we have a torque of 1500 going this way, and a force of 10,000 newtons going this way. And then the internal tension and internal torque. So Newton's second law says RA 0 plus negative 10,000 0 plus T 0 equals 0. So T is equal to negative RA plus 10,000. And then the moment equation. We have torque A plus 1500 plus the internal torque is equal to 0. So the internal torque is equal to negative torque A minus 1500. And these two are valid on the interval x between 1.5 and 2. Okay, so now we can do the two constraint equations. The total elongation has to be 0. That's because of the two fixed joints at the two ends. So that says that the internal tension on that first part, that's 1.5 meters long, times the length divided by EA, plus the internal torque on the second part, times the length of the second part over EA, they have to add up to 0. So, let me write it like this. So on that first piece, the piece that the first cut represents, delta 1 is equal to P1 L1 over EA. And that is negative RA times 1.5 divided by EA. I gave a Young's modulus for this. It turns out that for all of this stuff, that's just going to cancel. So I'll just leave it like this, but you could put that number in. And then the elongation on the second part is the tension on the second part times the length of the second part over EA. And that is the quantity negative RA plus 10,000 times the length of 0.5 divided by EA. And now we just say that if you add these two up, you have to get 0. So if one compresses, the other one has to stretch. So negative R, let me write this, negative 1.5 RA minus 0.5 RA plus 5,000, and it's all divided by EA, has to be equal to 0. So you can multiply both sides by that and get rid of them. And you get that 5,000 is equal to 2 RA. So RA is equal to 2,500. And now we can take this, go back up to, any of these steps, any of our free body diagrams. We got a positive value for RA, so that means that at this end, the force is pushing that way. And we can go to the statics equation now and calculate RB. RB is 10,000 minus 2,500, so RB is 7,500. And then the total angle of twist has to be 0. Yeah, I was just going to do all the internal, calculate the loads the reaction loads and then go and do the stresses after. But yes, you could use these now and calculate the stress due to tension. Okay, so the total angle of twist must be 0. Phi1 is equal to the torque on section 1 times the length of section 1 divided by G times I sub P. On that first section, go to cut 1, and the torque is equal to negative torque A. And the length is 1.5. The angle of twist in the second section is the torque on section 2 times the length of section 2 divided by GIP. And that's equal to, so go to the second cut. The internal torque is negative TA minus 1500. The length is 0.5 divided by G I sub P. And now we say that phi1 plus phi2 have to be equal to 0 because the two endpoints can't turn because of the fixed joints. So we have negative 1.5 torque A minus 0.5 torque A minus 750 divided by G I sub P is equal to 0. And you can multiply both sides by G I sub P. And you get that negative 750 is equal to 2 torque A. So the external torque A is equal to negative 375. And then you can go back to the statics equation. They have to add up to negative 1500. So the torque at B has to be negative 1125. Any questions about that? So that's the statically indeterminate part. And then from there, you just, depending on where in the member you need to calculate the stress or the strain, the internal load, we're looking for, so let's see, part B, we want the stress tensor x equals 0.5, the way I have it drawn. So it's 0.5 meters from the ground. And so from cut 1, we know that the tension at x equals 0.5 is equal to negative RA. And now we know what RA is. RA is 2,500. So the internal tension is negative 2,500. And also from cut 1, we can get the torque. torque A is negative 375. We know from cut 1 that the internal torque is the opposite of that. So the internal torque is positive 375. Yeah, you got to be careful with those signs for sure. That can very easily mess you up. I didn't have anywhere near that. Okay, so now that we have this, we know that the stress tensor total is equal to the stress due to tension plus stress due to bending moment plus stress due to shear force plus stress due to torque. There's none of this, so the only two we have to calculate are these. So the stress due to tension is the internal tension divided by the cross-sectional area. And I guess I must have given a cross-sectional area in class. Okay, so we got negative 2,500 divided by 0.002. 1, 2, 3. Oh, that's a radius. Oh yeah, that's right. 0. I know, that was that one, that's right. Yeah. Okay, so 0.00125. And then what do you get for the value? It's 10 to the 6. And so the stress tensor due to tension is negative 1.989 times 10 to the 6, zeros everywhere else. Yes, that is quite likely, I would say. Not this question, but some kind of statically indeterminate system. Oh, yeah. And so then we need the stress tensor due to torque. We know that the way we do that is we calculate the XY torque in this capital coordinate system where the z-axis is pointing out to the point that we care about. And that's equal to torque times rho divided by I sub p. I sub p is, I think, pi over 2 times the radius to the 4th. Okay. And the point we want is all the way at the outer edge. Rho is 0.002. And the torque is 375. So positive 375 times 0.002 divided by 2.513 times 10 to the minus 7th. Oh, not 0.002? I thought that sounded like a pretty skinny thing. Is that what I wrote up before? I guess, okay. Okay. And what do you get for that? All right. So now we have to think about what we calculated. So we have this stress tensor in the capital coordinate system that is 0, 2.984 times 10 to the 7, 0, 2.984 times 10 to the 7, and then zeros. That coordinate system has the z-axis pointing this way and the y-axis pointing this way. And so we want to go from this coordinate system to this one. Although actually in this problem, I mean, I would suggest just doing it the same way every time, don't get caught thinking too much. But we could just, since the only other element we have is the XX normal stress, we could just do it all in this coordinate system, add it now, skip the rotation matrix, everything would come out the same. Our maximum shear would come out the same, all that kind of stuff. But so the only time you need to do this is when you're adding shear elements in one coordinate system to shear elements in another coordinate system. You can't add like elements if it's not the same coordinate system. But, okay, yeah. But let's do it.
So no rotation.
You could do it with no rotation, but let's do it anyways, because I would recommend just do it. Instead of sitting there for 10 minutes, thinking like, oh, I'm just not going to do it. And then like, can I do it? Do I have to? Just don't do it. Just do it the same. Okay, so what's the angle of rotation here? Right, so theta is equal to negative 90, and about what axis? Yep. So the rotation matrix is 1, 0, 0, and then zeros down here. And then cosine of negative 90 is 0. Sine of negative 90 is negative 1. Positive 1, 0. In college physics, I have. I don't know. Because the thing is, like, the people taking this class, it's like, you've taken a lot of stuff for one thing, and then also, like, you pretty well have accepted by this point that this is going to be important type stuff for you to know, But like in college physics, it's all people who want to get into like some program in radiation technology or something, And their program just says you need to take physics, and they haven't taken math in forever. And so, like, if it's hard for them, they just get so mad that they have to do it, And so, yeah, I've had those people freak out and like cuss out other people in the class and storm out, and I don't like that. That's not my favorite thing. People screaming. I love putting stuff on YouTube. Oh yeah, I've had somebody like push back the chair, like, like, you stop muttering or whatever. But it's always college physics. I haven't ever had that stuff happen in engineering yet. Okay, so sigma is equal to Q times sigma XYZ times Q transpose. And let me think about this. What's that going to do? I think it will just switch the So this, the x element will still be the same. Oh, well, I guess we wouldn't have added it yet. I think this is going to just switch it to the xz element and make it negative. Does it make it negative? Just switches it. Okay, so no, that's not the 45. We haven't done the 45 thing yet. The 45 thing is after you have the principal stress tensor to get the stress tensor with the maximum shear stress. 0, 0, 2.984 times 10 to the 7, 0, 0, 0, 2.984 times 10 to the 7, 0, 0. Where? Oh, because it's negative and I didn't put it in here. Okay, yes, thank you. So let's put them in. So these should all be negative, and then these should be negative too. And this is the one just for torque. And so now the total is, what was it, 1.989 times 10 to the 6, 0. And that one's positive, negative. And then negative 2.984 times 10 to the 7, 0, 0, 0. Negative 2.984 times 10 to the 7, 0, 0. Now, so that's the stress tensor. I think the last, oh, it does ask for the principal stresses. Even if it doesn't ask for the principal stresses, if it asks for the maximum shear stress, you need to find the principal stresses first. So what are the eigenvalues for this? It's going to be, Scott knows what it is. It's like basically a positive and a negative 3 times 10 to the 7. Some people did. A couple of people did. Okay. Okay.
Oh, shut up, Fred.
So now this is where you use Ed Normandale.
Oh, yeah.
Oh, yeah.
The first test, I got 100% and everybody else like.
Oh, yeah.
It's so bad that we have to.
And you were mad.
And I was mad, and I'm like, okay,
Yeah. Right. Yeah.
And then later,
Huh.
no, I had to retake the fucking test.
Huh.
You're mad about people taking it?
Yeah, school is stressful, man. I don't know what to say, but try not to do that.
What if I do that at the U?
I'd just say try not to do it.
Have you ever bumped?
No,
Not once.
internally, not visibly. What would happen at the U? It depends very much what class it was, but mostly you'd just be ostracized. I think, I don't think much would happen. Everyone would just make a mental note to sit at a different spot of the classroom. Right. Yeah, you don't. Okay, so now we do the 45-degree rotation. And the key thing is to choose the right axis. So there are three eigenvalues, this one, and this one. One's the maximum, one's the minimum, and we want to rotate about the middle one. So those three, what's the middle one? 0. So we want to do a 45-degree rotation about the z-axis. Yep. The axis that corresponds to the middle eigenvalue. So this is a big positive, this is a big negative. 0 is in between those two. Oh, yeah. So we want to do a rotation about the z-axis. Okay, well, don't do that.
And like if you had two negatives and a 0, you want to go
right.
to the middle.
That's right. Yes. So now for this one, our rotation matrix is 0.7071, 0.7071, 0, negative 0.7071, positive 0.7071, 0, 0, 0, 1. And if you do that, so now the stress tensor with the maximum shear stress is Q times the principal stress tensor times Q transpose. And I'm not going to do that calculation, but we do know that what it's going to give us is a maximum shear stress of 2.886 times 10 to the 7th minus a negative 3.085 times 10 to the 7th divided by 2, which is almost exactly 3.0 times 10 to the 7. .986 times 10 to the 7. And then this is the thing that you would compare for your material, the number of, the loading cycles that you're dealing with or whatever. You know that this, you have some value that you don't want to exceed for your shear stress, and this is what you compare to it. Yeah. Any questions about that?
So what's the norm? How do we find the normal if we didn't have faith in our calculations beforehand?
What normal?
Well, it says the normal stress. If you don't know what you're talking about, with both normal and shear stresses.
Well,
shear stress.
Okay.
Well, that's
the normal stresses are. So where's our? Okay, so here, so after doing all the stress calculations, here was our stress tensor. The normal stresses are the diagonal elements, because if you draw the stress cube, the stress element, those are the ones that are perpendicular to the faces. And then all of the off diagonal elements are shear stresses. And so if you would have said, if you would have done everything and didn't get the answer and then decided to just give yourself stress tensor to start with that only had diagonal elements, you'd be skipping a step that I wanted to see you do. That's why I said, be sure you have shear stress elements too. Any other questions about that? Okay, well, thanks for taking my deform class. Yes. Oh, yeah, that's a good question. So office hours. Next week. Monday and Tuesday are going to be my usual ones. So that's going to be from 11. So 11 to 11:50 a.m. in the tutoring center, both days. And then Wednesday and possibly Thursday, I'll have to put that on D2L, but this will work for Monday and Tuesday anyways. But yeah, I'll post that in the notifications on D2L. Okay. See you next week.
It's not really